right there. So this is a talk on partial volume correction using this thing called the spatial GLM. And this is important because you're talking when you talk about layers, you're talking about very very thin slices of tissue in the context of like relatively large voxels. So in this, I'll go through what partial volume effects are. I'll talk about fixing partial volume effects using this spatial GLM. I'll talk about going through laminar analysis and the limitations of the spatial GLM, especially for laminar analysis. So partial volume effects come in two flavors mostly. There is something called the tissue fraction effect, which happens at the edge of a region of interest. And of course, laminar analysis, basically everything is going to be an edge. Something else, which is blurring and smoothing, which may or may not be an issue for laminar analysis. And then just why partial volume effects are a problem, which may be obvious. So the tissue fraction effect. So here's a 1 millimeter anatomical where we've used FreeSurfer to create surfaces, and then I've mapped them onto the fMRI, which is a 2 millimeter voxel size. And what I'm going to do on the next slide is just zoom into this little box here. And so here's my little box. You can see that it's all gray. Each one of those little boxes here is 2 millimeters by 2 millimeters by 2 millimeters. This yellow line is the white surface. This red line is the peel surface. So everything in between them are gray matter. And then everything on this side is white matter. And so you can see that this particular voxel is cut roughly in half by the white surface. So signal originating, or that you have signal originating from white matter and gray matter inside of this voxel. So that voxel contains like two signals in it that are just averaged together to give you one value that you get out of that voxel. So if we knew how much that was, then we could say that the fraction of gray matter inside of that voxel is 0.4, or 0.5, or 0.7. And that's where I get this map here. So the color scale that you have here goes from 0 to 1, and the color indicates how much gray matter is there based upon the amount of how that voxel cuts through the surface. So like this voxel here is almost entirely in gray matter, so it's a bright yellow. This voxel here is very close to being fully in white matter, so it's basically this dark red color here. And you can do this at every single voxel, and you can create maps in this way. So one question is, how do you determine what this tissue fraction effect is? And the way that I do it in FreeSurfer, including PetSurfer, so to give you a little bit more of a background, this type of partial volume effect thing is much, much worse in PET than it is in fMRI. And I have something called PetSurfer, which does basically integrates FreeSurfer and PET analysis. And so I kind of cut my teeth on partial volume correction using PET. And that's why what these references to PetSurfer are. So in PetSurfer, which can be used also for anything ASL, fMRI, whatever, the way that I do it is to just create a finer grid in each voxel. And then all I do is to count the number of squares that are inside or between white matter and gray matter, and that is the gray matter tissue fraction effect. And so then that's how I compute this number. There are other ways to do this. So Van Morik used a planar approximation. So the surface, of course, is like the smooth thing that's going cutting through all of your voxels. And so if you just, if your voxels are small enough, then the surface is approximately a plane. And so once you know where that plane is cutting through, then there's an analytical formula that you can use to compute the partial volume, the tissue fraction effect. So the other type of partial volume flavor is blurring or smoothing. You can see it here in this PET image. So this is FDG, fluoride dioxide, glucose, basically radioactive sugar. And as it comes through the PET scanner, this is what the reconstruction looks like. So you can see that it's very, very blurry. It's essentially like taking your volume and smoothing it with a Gaussian filter. So as I said before, this is generally not a problem in MRI, but as we start to try to squeeze out more and more resolution, you might have to worry about something like T2 star blurring, which can cause a little bit of blurring in the phase encode direction due to the T2 star effect. So both of these things, it's possible that they are present, and these methods for correcting them will work on both of them, basically. So in the problem that you have with each one of these is spill in and spill out. So the spill in is signal from an adjacent ROI that spills into a given ROI that falsely increases its signal. And then spill out is where you have signal from a given ROI that spills out of that ROI, falsely decreasing its signal. And so you get these complicated mixing effects depending upon how much activation is inside each particular region of interest that you're interested in. So there are lots of ways to correct for partial volume effects. As I said before, in PET, this kind of thing has been going on for now over 30 years, if you go back to Meltzer, 1990. These are voxel-based methods. What I'll talk about today are these region of interest-based methods. So starting back in 1998 with Rousseau, who developed something called the geometric transfer matrix. And then the same year, there's something called the symmetric geometric transfer matrix. And Chappell, working with Mark Woolridge at Oxford, developed a similar method. And then Van Moort came out like 4 years ago with the spatial GLM. Mathematically, all of these methods are identical. They're all just spatial general linear models. So I'll go through what these things look like and try to break it down for you. Oops. Okay. So here I have a toy image where I have two regions of interest. Region of interest 1, region of interest 2. And the activity in region of interest 1 I've labeled as beta 1, and the activity in region of interest 2 I've labeled as beta 2. So this is an unknown image. This is the perfect super high resolution image. I don't know what beta 1 is, and I don't know what beta 2 is. And these are the unknowns that I want to discover using partial volume correction. So when I actually acquire the image, what I get is not this nice, crisp, beautiful image, but something that's a little bit blurry. So if you think of having a tissue fraction effect model and a smoothing model, this is the acquisition model. How is this image acquired? And so that includes this tissue fraction effect. And if there's any smoothing in there, then it would include that. And so what you get is this blurred image where you have spill out, say, from this big white ROI into background, and from this big ROI into ROI number 1. And then you have spill out of ROI number 1 into the background, and you spill out and back into ROI number 2. So to compensate for this, first thing that we would do is to create two segmentation images. So the first one is a 1 everywhere I have the first ROI, and 0 everywhere else. And the second one is basically just the opposite. So I call these Z1 and Z2. The next thing to do is to apply your same acquisition model to it. So the tissue fraction effects and smoothing to give you these blurry binary segmentations. So these are going to be values between 0 and 1 that indicate how much of an effect is there, taking into account the tissue fraction as well as any spatial smoothing. So if I knew what beta 1 and beta 2 were, then I can multiply them by each of these images, add them together, and I'll get my actual measured image. So then the problem is, how do you find beta 1 and beta 2? And if you look at this, just takes the form of a general linear model where y is my acquired image. X1 and X2 are these tissue fraction affected and smoothed binary images of each of my ROIs. And beta 1 and beta 2 are the unknown activation levels. And so you can take this and combine it together to the familiar form of y equals to x times beta plus whatever some noise term is. And now I can simply solve for the betas by inverting the GLM through the standard GLM equation. And of course, you can do all the other stuff that you would do with GLMs. You can compute a forward model, a residual area, a residual variance. You can actually compute p-values for those for these betas as well. So in the end, what it looks like is something like this. So you would have this tissue fraction image. You have a segmentation, such as the APARC plus ASEG that comes from FreeSurfer. This has 109 labels in it. And in this particular case, it has something like 160,000 voxels. So in this y equals x times beta, y is 160K rows, which is a number of voxels. And then if this were fMRI, you might have multiple time points. So it's y is a matrix of number of voxels by number of time points you would have. X is also number of voxels, and then in the rows, and then the columns, each regressor is the tissue fraction effect for each region of interest. So in this case, it would be 109 columns. And so beta is this 100, will give you the 109 values for each ROI corrected for this partial volume effect. So what is the spatial GLM doing? It's subtracting out the spill in from nearby ROIs, and it's adding the spill out back in. And so it's doing essentially this this unmixing process. So that's the basics for this idea of the spatial GLM. So how does it apply to a laminar analysis? So when I wrote the FreeSurfer functional analysis stream, I actually had the ability to do layer analysis, back 20 years ago, whenever I developed it. And the way that I would do it would just be to create surfaces at different distances and then simply sample the fMRI at each of the vertices and surfaces points. This just requires interpolation, does not do anything in terms of accounting for partial volume effects. And the results look something like this, where each one of these different overlays is a different. Now, I wouldn't go off and say layers. It's more just surfaces that have been projected to different depths into cortex. So 0 is right at the white surface, 1 is right at the peel surface. I don't know why there it is. 1 is right at the peel surface, and then these are fractions of the thickness. So this is just going and interpolating, trilinear interpolation at each one of those different surfaces. So a different way to do it would be an ROI analysis, where I take those surfaces, however I create them, and I know that there are different ways to do that, and I can overlay them onto this region of interest map, for example. If I zoom in to this region here, you can see I have this brown region of interest and this green region of interest. And so for a layer analysis, what I would do is to take this brown region of interest and divide it up into 3 different regions of interest. So I'd have one for the first layer, one for the second layer, one for the third layer. And so instead of having one ROI, now I have 3 ROIs. And I would do the same thing with the green. So instead of having 109 segments in this volume, I'd have 245. So 245 labels, and so 245 betas. And this is basically the approach of Van Mork in 2019. So Van Mork used this method. He started off testing it by generating a simulation. So this is kind of like a simulated cortex with 6 different layers. And this was the overall ROI here shown as kind of this gray transparency on top of it. And so he applied this method of the spatial GTM. And to test it, what he did was essentially to go into a layer and set that layer value equal to 1. And then apply the spatial GLM to it, or do an interpolation on it, and to see, okay, what do I get in that central layer? And what do I get at the adjacent layers? So perfectly, it would be just a 1 at that layer and then a 0 everywhere else. So, and he tried it with 0.5 millimeter voxels and with 1 millimeter voxels. And so these results, I think, look pretty good. So if you're looking at this, basically a point spread function here. So ideally, it would be 1 at the center and then 0 off to the sides. And so what you can see is when you use an interpolation method, you get a slightly higher value in these off bands, indicating that there is spill out. So if it's not 1 and 0 on the side, then you have spill out. So you're not quite at 1 here at the center, and then you're not quite at 0 off to the sides. So that indicates a spill out. At 1 millimeter, that difference is even bigger. So the spatial GLM, which is shown here in green, is still very close to 1 and fairly close to 0 on the sides, but the interpolation methods perform very poorly. So this is an indication that the spatial GLM is doing the right thing. One thing to note is that you have a little bit of an undershoot here, and that's going to possibly create some problems. So on real data, they used ex vivo data, and I'm sorry, I forget what the actual resolution of it was, but they labeled this V1 area. And then what they did was to use the spatial GLM and the interpolation method to look at the profile, the intensity profile. So the horizontal axis here is the depth from white matter, I think, if I remember. So you can see that you have these changes. And what's interesting, and these are three different cases. So what's interesting is that you're really not seeing much of a difference between the interpolation method and the spatial GLM. And you might be seeing like a little bit of ringing artifact here in the spatial GLM. On real data, they had some data that was 1 millimeter, essentially resolution, and they went back to the calcrine sulcus and they created layers of surfaces. And they basically did the same thing. So they looked at having just 2 layers and like 4 layers and 6 and 8 layers, and solved the spatial GLM and compared it to the interpolation. And once again, you can't see all that much difference. But one of the things that you notice is that the spatial GLM is starting to become very noisy once you start dividing it up into these finer and finer levels. And that's because that there are some limitations to the spatial GLM. So you basically have a design matrix, and probably you're used to a design matrix from temporal analysis, where you'd have your time course and you'd say that time course is equal to some weighted combination of regressors, and then those regressors form your design matrix. You solve for that design matrix to give your regression coefficients, which are your hemodynamic response amplitudes. So this is basically the same thing, but it's happening in space rather than in time. So, but it's constrained by all of the other constraints that GLMs, everywhere, no matter what the context, are constrained by. First of all, there's a hard limit on the number of ROIs. It must be less than the number of voxels. Okay, it's not a big limit because you typically have hundreds of thousands of voxels and maybe on the order of less than 1,000 regions of interest. But the real problem comes to when you form these regressors. So those regressors, if you have a GLM, once the regressors start becoming collinear, then the conditioning of the GLM becomes very poor. And so when you try to invert an ill-conditioned general linear model, an ill-conditioned design matrix, you start getting into noise amplification. Or at least you're not getting the type of noise reduction that you would normally get with averaging in the GLM. So these columns are going to become start to become collinear when you get to smaller and smaller ROIs. And that's going to happen with these cortical ROIs because they'll become very, very thin. Actually, the cortical ROI, the cortical layer, setting up different layer as a different ROI is probably the worst way to do this. It's like the worst shape for creating these collinearities in the spatial GLM design matrix. And so it's kind of like perfectly oriented towards amplifying this type of noise. So other limitations are the GLM assumes this constant signal within an ROI with Gaussian noise distributed within it. And this isn't always the case. You might have very big ROIs and you need to make them smaller, but now if you make them smaller, you run into this first problem. There could be blood vessels in there, and these things can mess up the unmixing. So it's counting on being able to estimate how much spill in and spill out there is and to compensate it for it in that way. And just to show you a rather gross example of it, consider this first model that I was solving where white matter is like this ginormous region of interest. So what the spatial GLM is going to do is it's going to estimate one value for white matter. And then it's going to subtract that from all of the adjacent ROIs scaled by the spill out. And so the value that you might have in the middle of white matter might be very different than the value that you would have still in white matter, but kind of close to cortex, depending upon what the vessels are. So, that might not be a good thing to have. So one thing as you can do is to break up white matter into many smaller regions, such as I've done here. This is the WM part that's created by FreeSurfer. So instead of 245 segments, I have 313 labels in there. So this is going to make it a little bit more specific to the white matter ROI specific to the cortical ROI. But again, you're increasing the number of segments and you're increasing the collinearity in the design matrix. So there's basically no free lunch on that. So to conclude, PVEs, partial volume effects, take the form of this tissue fraction effect where a given voxel is spanning two different tissue types or two different ROIs, and blurring. Blurring might not be important in MRI, or it might be, depending upon how much T2 star blurring you have. We assume that this mixing is linear. Is that really going to be the case? I'm not entirely sure. I'm a little dubious of it in PET, and it wouldn't surprise me if that was an assumption that was violated in MRI as well. The spatial GLM is this unmixing process where it's estimating what the spill in and spill out are, and then either subtracting them off or adding them back in as necessary. For laminar, you can create ROIs for each layer and then simply solve this spatial GLM. It works well in simulation, but it was less clear in this data from Van Morik. And why that is a little bit of a mystery to me. And it seemed like, looking at the paper, it seemed like it was a little bit of a mystery to them as well. So keep your eyes open for more research on this. But I want to point out that partial volume correction works extremely well in PET and in ASL and is used routinely for that. You have to keep the conditioning of X in mind, so you can't have arbitrarily small ROIs with arbitrarily thin layers, or else you'll get this noise amplification. And that's it.